Hi, I'm Professor Craig Putnam from WPI's Robotics Engineering program, here with another in our series of videos on op-amps. In this video, we're going to look at another application of op-amps, something called differential amplifiers. If you remember back to the first of our series of videos, we started off by looking at an op-amp in the configuration of a comparator. That's a pretty limiting kind of case. If you recall, the output voltage was going to swing all the way into one of the voltage rails, either the high-end rail or the low-end rail, depending on a tiny change in the voltages between the two inputs. So an op-amp that's configured as a comparator is, in fact, a differential amplifier, but it's not terribly useful in that the very high gain that it's got always causes the output to be either one extreme or the other of the rail voltages. What we're going to look at now is a more refined way of handling that situation. Again, we want to be able to compare the two input voltages, and specifically we want to look at the difference between those two input voltages. But in this case, what we want to do is we want to better control the output voltage, and we want ultimately to have the output voltage be proportional to that difference in the input voltage, but stay within a reasonable range, for example, 0 to 5 volts. The way we are going to accomplish this is we're going to use a combination of the circuits that we have already seen for the inverting and the non-inverting op-amp. We're going to kind of put them together, a little bit of each, to form a new kind of circuit, which is called a differential amplifier. Let's start by examining a simple op-amp circuit that's capable of accomplishing this goal. As you can see here, there's a feedback resistor, R2, connecting the op-amp's output back to the inverting input. There's also a resistor, R1, in series with the voltage V1, which is feeding the inverting input. All that looks much like what you would have seen on an op-amp setup in the standard inverting configuration. Note, however, that the non-inverting input is not grounded as it would be for the standard inverting amplifier. Rather, we have the other input voltage, V2, feeding a voltage divider consisting of resistors of values R1 and R2 again. The inverting input voltage is the voltage drop across the resistor R2 of this voltage divider. This circuit is called a difference or differential amplifier. It has some interesting and useful properties that we'll now explore. There are several ways to handle the analysis of this circuit, but an easy way to proceed is as follows. First, we'll determine what the voltages are at the two input terminals, the inverting and non-inverting inputs. Recalling the summing point constraints we discussed in an earlier video, we know that the feedback in the circuit will drive the input terminal voltages to be the same value. In other words, V plus will equal V minus. Finally, we can apply KCL at the inverting input terminal. From that, and again using the summing point constraints, we know that I sub 2 will equal negative I sub 1. Let's start by developing an equation for what's happening at the non-inverting input terminal. Given the voltage divider that's connected to this terminal, it should be apparent that the following equation will relate the non-inverting terminal voltage, V plus, to the input voltage, V sub 2, and the resistors forming the voltage divider. Now let's apply the assumption that the two input terminals must have the same voltage. In other words, V plus must equal V minus. We can now calculate the voltage drop across the input resistor R1 that's in series with the voltage source V1, and from that we can generate the following equation for the current I1 passing through that resistor. We get the following. We can also generate a second equation that relates the current I sub 2 through the feedback resistor R sub 2. In this case, we get the following. Finally, we know that I sub 2 has to equal negative I sub 1. We can now massage these four equations together to produce the following equation. Now that's a little bit messy, but after a bit of algebra, you can reduce this down to the following very useful result. And what we have here is we can see that the output voltage is going to be proportional to the difference between V2 and V1 times some gain factor, and that gain factor is going to be given by the ratio of R sub 2 to R sub 1. So we have here now something really useful. We have a circuit where the output voltage is proportional to the difference between the two input voltages, But beyond that, we can control the gain of the circuit by adjusting the values of the resistors R sub 1 and R sub 2. Let's now look at some examples of the difference or differential amplifier in operation. In the real world, we want to be able to take some perhaps small voltage level signals, perhaps coming from an electrocardiogram, something like that, and amplify the difference between them. Now, the difference amplifier or differential amplifier should be ideal for this. We can control the gain. We have the difference of the two voltages that will be taken into account. But the real world's a messy place. One of the things that's going to happen is those leads on your electrocardiogram, for example, they're going to pick up electrical noise from the lights, from other circuitry that's around the system that you're interested in. And what will happen is that that noise will get picked up by each of the leads. So we're going to make a couple of assumptions here. First is we're going to assume that these leads are, let's say, the same length, and they're fairly close to each other. These are quite reasonable approximations and assumptions to make. Given that situation, it's fair to assume that the noise signal that's picked up in each lead will be the same, or very nearly the same. So we have our signals that we're interested in V1 and V2, and then we're going to have some noise that's added to each one of those, and we're going to assume that the noise is the same. So now we're going to actually explicitly move to the situation where we're going to assume that our input voltages are in fact functions of time. So we're going to say V sub 1 as a function of time, V sub 2 as a function of time, and V sub noise, or V sub n, as a function of time. Let's model this as follows. We have our desired signals, V sub 1 and V sub 2, and we're now explicitly letting them be time varying. Let's also suppose that there's some electrical noise that's being picked up. And here's our equation. V sub n of t equals some capital V sub n, some voltage amplitude, times the sine of 377t plus phi sub n. The 377t represents the 60 hertz sinusoidal signal, and then there's some phase offset phi sub n. And as before, we're going to assume that the same noise signal is being picked up on each input of the differential op amp. So what we have then is the signals V sub 1 of t plus V sub n of t, and V sub 2 of t plus V sub n of t. Substituting these input signals for our previous ones, we see an interesting result. The noise signal cancels out. We get exactly the same result that we had previously. That's pretty cool. This is an example of what is called a common mode signal. The same signal, the noise in this case, is being picked up on each of the inputs. By contrast, the signals V sub 1 of t and V sub 2 of t are called the differential mode signals. So we've got this combination of a common signal, the noise, and the differential signals, which are the signals that we're interested in. In real-world differential amplifiers, you don't get this perfect result where none of the common mode signal shows up in the output. The extent to which that common mode signal does show up in the output is called the common mode rejection ratio. That's kind of an advanced thing. We're not going to go into that at this point, but I mention it just to be complete. In the differential amplifier we've looked at so far, we've used a single op amp, and both of the input signals are amplified by that same op amp. Now, a refinement of this circuit is where we introduce some additional op amps, two of them to be specific, one each for amplifying the two input signals, and then a third op amp is used to actually do the combining where the difference is calculated. A simplified version of this 3 op amp circuit looks like this. Without getting into the details of the derivation, the gain of this circuit is given by the following equation. Now you'll see that we've got resistors R sub f and R, and then R sub 1 and R sub 2. Let's make a simplifying assumption here and say that if the resistors labeled R sub f and R are equal in value, then this equation simplifies down quite a bit, and we get the following. This is a much nicer system to work with. There's a couple of advantages to this 3 op amp system. The first is that there's a better impedance isolation between the two input signals than in the single op amp difference amplifier. The second advantage is that the overall gain of this amplifier circuit, and this is called an instrumentation amplifier circuit, by the way, the overall gain can be determined by selecting the value of just one resistor, R sub 1. We can have R sub 2 be fixed in this case. In some instrumentation amplifier circuits, that one single resistor that you adjust is an external resistor that you supply to the circuit. Well, that's it for this video. Hopefully you now understand a bit more about difference or differential op amps and the instrumentation amplifier. In the next and final video, we're going to take a look at a more advanced topic called integrators and differentiators. See you then.